Hi, this is a little extra help for completing the Section 7 reflections for L07, average velocity, instantaneous velocity, and PT graphs. In this particular section, what you're being asked to do is to practice the use of determining average velocity using the slope of a secant line, and then also determining a good approximation to the instantaneous velocity using a different type of secant line. Here are the two questions that refer to average velocity, and here are three questions down here which refer to instantaneous velocity. In all cases, we're looking at the position time graph over on this side. And I've put some little tables down here to help me while I'm showing you what I'm going to do. I'm actually going to use different numbers from here, so you still have some to work on. What we're going to do first is I'm going to, instead of finding the average velocity over the time interval from 2 seconds to 6 seconds, I'm going to find it from the interval 3 seconds to 10 seconds. First thing I'm going to do is I'm going to go down here and just remind myself that I'm going to go from 3 seconds to 10 seconds, because what I'm going to have to do is pick up one of these lines, and now I have to place one end at where the curve intersects 3 seconds and another one at where the curve intersects 10 seconds. So what I'm going to do now is I'm going to highlight where those intersection points are using these little circles that I've made for myself. And those points where the secant line is intersecting the curve, those are my ordered pairs for determining the average velocity. If I look at this one here, which is at 3 seconds on this axis, and now it's in position, it's at looks like 4 meters. So I'm going to put 3.4 meters here. And the position here is 2.5, 2.75, about 2.8 meters. I now come down here, and I'm knowing that displacement is d2 minus d1. It's going to be 2.8, which is d2, minus 3.4 meters. And that equals minus 0.6 meters. The time interval is going to be 10 minus 3, and that's in seconds, and that equals 7 seconds. To find the average velocity, I put the change in displacement over the elapsed time, which is minus 0.6 over 7, and the units are meters per second. Notice that the velocity that we'll achieve for the average here is actually negative, and that's reasonable when you look at the slope of the secant line. Next one I'm going to do is show you how to approximate finding the instantaneous velocity. And I'm going to look for the instantaneous velocity at t equals 3.5 seconds. That's 3.5 seconds there. And I'm going to pick up the green line, because those are the colors I've chosen for my two examples. And I'm going to come over here, and I'm going to go and try to find that slope. Now, how do I go about doing that? Well, what I'm going to do is I'm going to use a method where I go equal distances in time on either side of the point I'm interested in. So that would be, since this is 3.5, I would need to go to 4 seconds and to 3 seconds. So what I want to do is make sure the line goes through 4 seconds. So now that's intersecting here at 4 seconds, as you can see. And now I'm going to make it intersect the black line at 3.5. But I'm also making the line as long as I can, because by making it long, I make it more accurate. So there's the intersection 3.5. I'll bring this other little one along here. I may actually have to move the end of this one to get it down to 4. Yeah, there we go. So now you can see the green line is crossing the 4 there, and the green line, now I need to move it a little bit again. This might take me a little bit to get this done, but I will do it. Trying to do is to get the line to go through 2 ordered pairs here. One is at 4 seconds and one is at 3 seconds, which is midway, which is an equal distance in time on either side of the point I'm interested in, which is in fact 3.5 seconds. So I'm actually finding in this green section here the instantaneous velocity at 3.5 seconds. Now, why did I make this line much longer? Well, if I make it much longer, I can get a much more accurate number. So in this particular case, it looks like the line is actually going to cross 8 seconds and 5.2 meters. So that will actually be my second point, 8 and 5.2. And on this side, it looks like it crosses at 0 and 2.25. So I'll put 0 and 2.3. So now I have to find the change in displacement. Change in displacement is 5.2 minus 2.3 equals 2.9 meters. The interval is going to be 8 minus 0 seconds equals 8 seconds. So my instantaneous velocity is actually going to be also delta d over delta t in the limit that delta t goes to 0. So I'm using an approximation here because I'm not actually making delta t go to 0. Delta t is really 1 second because that's how I've drawn that line. But I choose points at each end of the line in order to make my calculation of the slope more accurate. That instantaneous velocity is approximately 2.9 divided by 8 meters per second.